Continuing on with our lens theme, we're now going to look at a property called depth of field. So far we've looked at bringing one subject at one distance from the camera into sharp focus onto the sensor. In this case it's the moon, and we call this distance from the sensor the plane of focus. So in this instance the plane of focus would be the moon, which is 250 million miles away, brought into sharp focus onto the sensor, and this area, the distance the moon is away, is called the plane of focus. So everything, whether the moon was up here or something else was at that distance, it would appear equally sharp as the moon does. Now if we focus closer, everything at that new focusing distance would be rendered equally sharp, and that would now be termed the plane of focus. Now at either side of that plane of focus, the detail of the image is spread out over steadily larger areas, appearing less sharp. So again, we're looking at these cones of light, these rays of light coming in a kind of cone shape from one specific spot on the scene, crossing exactly where the sensor is, and that is the plane of focus is sharply rendered onto the sensor there. Either side of the sensor, the image, if the sensor was moved to that position or moved to that position, would be rendered over a larger area, and it becomes progressively less sharp. And we call these areas circles of confusion, and if you look at them, it is a kind of circular shape spread out over a larger area on the sensor. So the further from the plane of focus, the blurrier the image becomes. Some parts of the scene will focus exactly on the sensor, okay, appearing very sharp, but others will be rendered more diffused. Okay, and the further away from the plane of focus, which is out there, sharply rendered onto the scene, onto the sensor, the further away from that, progressively these circles of confusion become larger. Therefore, it would appear less sharp on the sensor. Now there's a tolerance area that isn't perfectly sharp, but is sharp enough, and we call this the acceptable depth of field. Okay. In this instance, we could say that okay, everything that's sharply focused on the sensor is okay, and everything that's not quite sharp is also sharp enough. It looks reasonably sharp, and we call that depth of field. So depth of field is the area of the image between the closest and the farthest part that appears acceptably sharp. So here's our plane of focus. Everything further away that still appears acceptably sharp, and everything closer to the camera that also appears acceptably sharp will be in our range, what we call the depth of field, acceptably sharp. So the outer angles at which the cone of light approaches the sensor basically determines the depth of field. And again, I'm going back to these cones of light illustrations, trying to get across this idea that the greater these angles of cones of light, the less depth of field we're actually going to achieve on the sensor. Okay, so we've got quite a wide angly cone of light here. Okay, so if we remember back to the pinhole camera, where we have a very, very small aperture, the equivalent of a very, very tiny lens, there is there's effectively infinite depth of field, because the cone or shape of light coming in here is effectively zero. Okay, so we'd have everything that's at total distance, everything that's at the right height, and everything that's closer would appear equally sharp. However, because it's a pinhole camera, it admits very little light, and it's unworkable. So from that we can deduce that a large diameter lens produces a bright image but a shallow depth of field. Okay, so we've got a fairly shallow depth of field. But thinking back to the pinhole camera, if we make a small diameter lens, produces a dimmer image, in which case we need a longer shutter speed, but we get a larger depth of field. Okay, and look at the angles of the cones of light that are coming in for a large depth of field compared to a shallow depth of field. Okay, so if we imagine that that sort of distance there is acceptably sharp, we'd have to go back to this one here, same sort of distance, but look how further away each side of the sensor that becomes. So it means that it's a larger depth of field. Things that are further away from the red kite and things that are closer to the camera from the red kite would also appear acceptably sharp. Now, most modern lenses have what's called a variable aperture, and we can adjust the depth of field using a single lens. Okay, so here we have a lens with a diaphragm, a variable aperture diaphragm, almost at full aperture, so it's almost letting in the light from across the entire lens. Okay, and we have these very steeply defined cones of light. Okay, and this kind of illustrates that the lens is quite wide open. There's a diaphragm. So we've got a fairly shallow depth of field. Large aperture, shallow depth of field. Here we've got to close down that aperture, so it's a smaller hole, same lens but a smaller hole. Shallower kind of angles of the cones of light hitting the sensor. And here we got you can see the rendering of the diaphragm. It's closed down, and we get a larger depth of field because the diaphragm is, or the aperture is shut down. And if we close it down really far, same lens but only admitting light through the central portion like this, we get a much greater depth of field. And again, looking at these angles of light rays coming through, we can see that the narrower they are together, the less angle, we get a greater depth of field. Greater angle, shallower depth of field. And this kind of mental image is useful to remember because you can work things out in your head rather than having to remember key facts. A wide aperture gives you these steep cones of light, which means a shallow depth of field. A small aperture at a high f number like f16 produces a greater depth of field. So in summary, what affects depth of field? The lens aperture, whether it's fully open, in which case you get a shallow depth of field, really closed down, in which case you get a greater depth of field. The focal length of the lens. Telephoto lenses give you less depth of field for any particular aperture than wide-angle lenses. The camera's sensor size. Smaller sensor sizes emphasize the depth of field more than larger sensor sizes. In fact, when you get to very, very small sensor size, like on your phones and things like that, you'll have virtually unlimited depth of field, and there won't be an awful lot of focusing needed for that sort of size sensor. The distance to the subject being focused on. You'll find that when things are in the distance, you can get quite a considerable depth of field. You know, if you focus at a mile away, then things that are many miles away will be also in focus, and things that are like a quarter of a mile closer will also be in focus. Whereas if you're looking at something that's 10 millimeters away, then the plane of focus becomes so much shallower that it's maybe half a millimeter either side for the same aperture. And it's also down to your choice as to what you regard as acceptably sharp. It's a subjective assessment. So generally, for moderately close subjects, the depth of field extends 1/3 towards the camera and 2/3 away from the plane of focus. So if you're focused on a subject a meter away, then the depth of field, if you consider it acceptably sharp, it will extend 1/3 of a meter towards you and 2/3 of a meter away from that plane of focus, the thing that you got totally sharp. So hopefully you can now understand what depth of field is all about.